All right, hey, how's it going, guys? Happy Thursday. Again, I won't see you until Wednesday next week, so hopefully you get a chance to watch this video. Get used to me again, Mr. Fortin. But anyways, we had a short week this week, short week next week, and one thing that we didn't really have time to talk about in class was something called combining like terms. Now, I've kind of left that as a comment to several of your classwork. If you're writing a perimeter of a shapes of a shapes here of a polynomial, or writing an area, right? Remember, polynomials can be expressed as areas. But anyways, if you're writing that, you could write out your answers by just like, hey, counting the number of tiles if it's an area, or counting the outside. And just like counting every part of the outside if it's a perimeter. But chances are you would not write your answer as simply as you possibly could write it, okay? So what we're gonna talk about in this video today is something called combining like terms, because you're actually able to combine a lot of the pieces here. Here are a bunch of pieces, right? We have 2x pieces, another 3x pieces. We have a 3 piece, not 3 piece, we have 3 ones, right? That's 3 ones right there. Here we got 4x squareds, okay? And then we have a 10 ones, and then we have another x or another x here. So the idea is we want to be able to combine an equation an expression like this, where we're just adding them all together. Okay, so this is pretty easy. All these problems here in this problem are just adding things together. So we can combine our like terms and write our answer more simply, and that's what we're going to do today. Okay, so it says here, copy and simplify the following expressions by combining like terms. Using or drawing sketches of algebra tiles may be helpful. Yes, it might be. It might be here. And here I'm actually going to go to some algebra tiles online. Don't lose me here, right? Stay with me. Stay with me here. I know we're going to the tiles here because I actually want to show you this. Here I got problem A. Because if we had time in class this week, we would have done a couple problems very similar to this, okay? Again, we only saw each other twice this week for about a half hour each time. Not enough time to do this. It's a little bit less important to combine. Well, you know, it's easier, right? Combining like terms is easier than maybe what you did yesterday. So that's why I wanted you to do the area as a product and as a sum lesson yesterday. So we're still getting used to that here, okay? So check this one out here. So this is just another way to think about this. I want to represent this to you visually, that we have these tiles here. We can combine them, right? Combine them in a certain way. We can combine what's called the like terms, okay? Like terms, right? If I had to say it without tiles right here, this is how a traditional textbook would define the term like term with you, right? Learn term with you. Like term is same exponent, okay? Same exponent and same variable, okay? Same variable, same exponent. That's going to be the way we can think about our like terms, okay? So we can combine our y squareds, right, with other y squareds. We can combine our x's, x to the first power, that is, with our other x's to the first power. We can combine our x to the third power with another x to the third power, right? We can add them together. Here, this is 9x to the 0th power, technically. This is 10x to the 0th power, right? So what is x to the 0th power? You guys remember 0 powers, right? 0 powers are equal to 1, right? X to the 0th power just means 1, so 10 times x to the 0th power is just 10 times 1, that's 10. Anyways, 10 is the only thing that combines, we'll combine with 3 to the x to the 0th power. Anyways, same exponent, same variable, you can combine like terms. And let's just check it out here visually, number 1 here, because ideally we would have done this in class. You would have gotten a question like this. Well, say we take this polynomial. Sure, this is a valid polynomial, right? I haven't defined what polynomial is here, but it's many terms, right? Terms are separated by pluses and minuses, and we have a variable and an exponent usually, or we don't see the variable because it's x to the 0th power, that kind of thing here. So anyways, let's take a look at this one here and see if we can just do this here. So I'm going to do this the long way, which is with tiles. This is part of the reason why people don't like tiles in class a lot of the time, is because it just takes time. You're like, this is so tedious. So let's check it out here. Okay, so here we have a cluster of 2 x's. What does that look like again? We've been working with that in class. Right, we would call this into, if we had like a shape that uses both of these, we'd say, well, there's 2 x's. It looks like we also have a cluster of 3 x's here. Okay, how many x's total are we going to have? Pretty simple, right? In 1 second here, just wait for me, flatter me for a second. Watch this video. We have 5 x's. Look at here. So 2 x's plus 3 x's. Look, 1, 2, 3, 4. 5 x's. Remember, x's is your smaller dimension, smaller unknown. Remember, this is 1, that's 1, but this is 1, and that's x on the side here. 1 times x is x. Okay, so we have that 5, and then we have 1s. We have 3 more 1s in the expression. So what this question sort of also pointing out here is that this is a valid polynomial, right? It's written out like this. But it's messy because the like terms are not next to one another. We got a whole bunch of terms here, and it's all kind of scattered about. We have a plus 3x. Okay, I've already talked about that. I talked about 2x plus 3x, and then we have a plus 3 here. And now all of a sudden we're talking about x squareds in that expression. So this is messy. And there actually is a standard form, a way you'd standardize writing it. Like, that's definitely a question you might get is, write this polynomial in standard form. I'm perhaps going to talk about that a little bit later in this video. So here we have 4x squared. So let me put this one down here. Bear with me. I know this is pretty boring watching a teacher just kind of talk and read the whole thing here, but I think it'd be good if you guys just bared with me. We'll do it the long way, hopefully just this once. And then I'll show you a picture of the next one so that we don't have to do all this dragging here, okay? But I wanted to really emphasize this to you too, that here again, we're looking at 2x plus 3x plus 3 plus 4x squareds here. And now all of a sudden we're talking about ones again, right? This is messy the way that they wrote this out. 1, 2, 3, 4, and then finally 5. And you know what? I can just copy and paste these to get to my 10 ones. Okay, so here I got my 10 ones right here. And then we talk about 2 more ones. Oops. I'm going to copy this. And there we go. There's another one. And finally, 2 more ones here, okay? So you wouldn't say, like here, they're right next to one another, right? Like this is 10 plus 2, that equals 12. That's good here too. Hey, there's actually something else called, you may have studied before, there's something called the commutative property of addition. What commutative property, right? Going on a commute, right? You're commuting to work. What does that mean? You're traveling, you're moving, right? You're moving. So there's something called the commutative property of addition where you're allowed to, if you're adding, order doesn't matter. You can move things around, right? You can move things around as long as things are being added. We don't see subtraction here. We don't have to worry about that. We don't see division. We don't see anything else. We just see addition here. We can move stuff around. So you know what? Why don't we actually combine like terms here? Let's move things together. Well, these are next to each other. So that's going to combine to be 5x right here. Okay, there's 5x right here. So this is going to equal, let me type in here. We'll get your answer in a second. This is going to equal 5x. Right? That would combine to 5x here. And then we got our 3. So commutative property, let's move it over here. See how many ones we have. Let's combine our like terms. Okay, and it looks like we're going to have looks like I'm combining the 3 with the 2 right here, but I want to combine everything here. So combine the 3 with the 10 and the 2 with the 10. And 10 plus 3 plus 2 equals 15. We got 15 right there. Okay, so here I have 5x, and then I have 4x squareds. Okay, those were the only x squareds that we have here. So we'd already combined those like terms, right? X squared is a type of term, and any other x squareds would be a like term because it would have the same variable x and same exponent too. Okay, that's the criteria for being a like term. Same variable, same exponent. Put that in your notes, right? Put that in your notes down. It's an important thing to get. And then finally, last one here is that 10 plus 2 plus 5, which we have here, 15. And that's pretty darn simple, okay? So I actually, little bonus here, I wasn't planning on talking about this here. That's actually not how I'm gonna write my answer. I'm not gonna write my answer 5x plus 4x plus 15. I'm going to write it in standard form, an even more standardized way of writing this here. 5x plus 4x squared plus 15. And I'm gonna ask the question for you here too. Why can I make this a little bit more standardized, do you think here? Like, just think of logic. Math is reading and reasoning, so think about this here. Well, this is definitely more simplified. Okay, this is definitely more simplified over here than this, right? Here we're just showing 3 terms because we've combined all of our like terms. But do you think order matters? Order does technically matter, okay? So one thing that I'll see here, special bonus, is that we want to order from the largest exponent, the term with the largest exponent, okay? Order from term with largest exponent to smallest exponent. So what I'm going to get for my answer here is going to be 4x squared plus 5x plus 15. And we are good to go, okay? So that is standard form for writing out a polynomial here, okay? So I have an exponent of 2. Here, I technically have an exponent of 1. You don't have to write it out here, exponent of 1. And here, technically, I have an exponent of 0, right? Because 15 would be equivalent to 15 times x to the 0th power, right? Anything, this base here is x. Take that 0th power, that's 1, so this would still be 15. So exponent is 0 here, okay? So that's how I wouldn't write this stuff out with red here. I'd write this 4x squared plus 5x plus 15. There's your answer to number A, letter A, okay? Hopefully you're still watching this video, because I think I'm telling you some things like that I think would be helpful to everybody, even if you've combined like terms before. Okay, so anyways, let's check out B. Let's get that one done. I already have B set up here, so let's check this one out. We got to do 4x plus 4y squared plus y squared plus 9 plus 10 plus x and plus 3x here. And I got it set up already. 4x would be right here. 4y squared is right here. Well, that's nice. It's right next to another y squared. We can combine those like terms. We'll do that later. 9 and 10 are next to one another. And those are both 1s. Those are both like terms because they have or a variable would be x and to the 0th power. So here we have 9 and here we have 10. And then we have x and we have 3x. Cool, those can combine, okay? So rewrite the total area in the simplest algebraic form as possible. Well, all we got to do is combine our like terms, okay? Combine our like terms and then write it in the standard form, right? Write it in the correct order, right? With that ordering thing. So maybe we'll do that when we write in the answer, okay? So I already have my tiles up here. See, people would like using tiles if they didn't actually have to set it up with the tiles. If you have to set it up, then it gets messy, right? Because it takes a lot of time. It took me a lot of time to set this one thing up here. But now I have it. Look at this. I have it. I got it all set up. I can move these a little closer if I want because I can combine my 10 with my 9. I certainly can. And I'd have how many? Well, 10 plus 9 is 19. Like I got these 19 tiles together right here. So combining my 1s, I get 19. Combining my x's, I get 7x. Look, 1, 2, 3, 4, 5, 6, 7, 8. No, not 8. Oh, wait, no, 8. Yeah, because this was x plus 3x. My bad. So that is 8x here. So that little cluster over here was a cluster of 3 x's and then a 1x next to it here. So remember, when you see the 1 in front of it, that just means x, right? 1x piece. Okay, and then combining this is 5y squared, right? 5y squared. Okay, so this problem is dealing with x's and y's, and I forget. I think y comes before x, but we don't have to worry about y terms because we have y squared. So we'll definitely talk about y squared first because that has a variable with the largest exponent. Okay, so my answer to this one here is going to be 4y squared. No, not 4y. We have 5y squareds. Okay, I got 5y squared. And then I have 8x, so I'll do plus 8x. And then here I got plus 19, okay? And that's the simplest way that I can write that expression, this long polynomial, right? So many terms added together, we can combine those. We have 4x's, we have another 3x's, that's 7x. We have another 1x there, that's 8x, right? 5y squareds here, okay? So when you have common terms like this, you just need to add the coefficients. Those are called coefficients, the numbers in front. When you know what term it is, just add the numbers in front. And then if we don't see a number in front, it just means 1. Okay, so I got 4y squareds here. I got another 1y squared here. How many total? 5y squared, right? I got a 9 here and I got 10 here. Well, that's 9x to the 0th. 10 times x to the 0th. So that's just 9 plus 10, which is 19. This can be done a lot faster. So guys, let's wrap up here. I'm actually might do part C and part D. Well, at least I'll leave part D for you. I'm not going to do part D. So that's definitely going to be checked out here. So let's do this one here. And here, do you have to draw out these tiles? No, you know that by now, right? You don't actually have to draw it out. Sometimes it's helpful to draw it out so we're dealing with it and you see it visually. But the idea is, well, I have an x squared term. Look, I have an x squared term here. I have an x squared term here, an x squared term here. What can I do with those? I can combine them. Okay, they're all being added together, so they're all positive x squareds. Here I got 2 of them. I got another 3. I got another 4 of them. So how many x squareds total do I have? Well, 2 plus 3 is 5. Plus 4 would be 9. Okay, 2 plus 3 plus 4 equals 9. So I have 9x squared total. There we go. Okay, here I got a 30 here. Maybe I'll deal with 30s later. So I have an x term. That's what I'd write next. I don't have any other x terms here, so there's no like term to combine it to, right? There's no x to the first power anywhere else. This is my only x to the first power, so I don't have to combine that like term with anything else. I can just say it's plus x. Okay, here I got 30 and I got 14, so I do have some x to the 0th powers right there, or just 1's terms, we'll call them. Constants is the right word for that, right? If you're either a variable or a constant. This is a variable x. That's a variable expression, x squared. A constant is not a variable, right? We don't have a variable here. It's a number that doesn't change, right? X changes as you assign values to the variable. X squared changes as you assign values to that variable. Your constant here is 30, and this constant here is 14. So you're adding those two together, you're always going to get 44. And that's your answer to that one. Okay, thanks for watching there, guys. I think I'm going to film one more video that I would recommend watching of the very last problem on the problem set. And that was actually having to do with multiplying some of these polynomial expressions. Here, this one, we added polynomial expressions. So that's how we combine like terms. The other one, we're not really combining like terms. We're doing something just called multiplying polynomials. So we might have to distribute those. Anyways, watch that video later. Send me any questions if you have them. Thanks. Bye.